So moving on into our last section for the week, we're going to be talking here about rational functions, which we've seen bits and pieces of already. We just didn't properly define them in this way. When we talked about things with long division, we probably even wrote expressions that end up looking a lot like rational functions. But really all a rational function is just polynomial on top of another polynomial where the bottom one's not zero. Or we don't have zero in the denominator because that causes problems, as we've talked about before, where we have specifically seen these, just not in those terms, when we talked about compositions and divisions of functions back in chapter 2. And we're going to be talking about the same sort of things here as an introduction with these, because when we are dividing, we have to avoid division by zero, which means when we talk about the domain of a rational function, we have to be careful to avoid potential zero values, just like we did back in chapter 2. And like I said, that's where we'll start here with a couple of quick examples. So to start here, we want to find the domains of the rational functions x squared minus 9 over x minus 3, 5x over x squared minus 3, and 3x over x squared plus 3. And for each of these, starting with that first one, what we're going to want to do is just identify the potential locations where the denominator can be 0. And in that first case, that means what we want to avoid is x minus 3, the denominator, equals 0, or in other words, x equals 3. So if we want to define the domain here, it's pretty straightforward. The domain of f, which we're going to use that d notation that we had before, is going to be, actually I shouldn't use an equal sign there, maybe I should use something more like a colon. We can write that either as the set of all real numbers without 3, because it is every real number other than 3, or if we want to in set builder notation, that's the set of all x's such that x isn't 3, or if we really want interval notation, the set from infinity to 3 without 3, along with, that is union, the set from 3 to infinity, still without 3. Again, these are just 3 separate ways we can say any real number except for 3. Then for the second case, again, when we're finding domains, we're trying to really define the things that it can't be, because those are often easier to identify than sort of getting that double negative type of language to find the domain. So here, I don't know why I started with an I, we want to avoid that denominator being 0, so we want to avoid x squared minus 3 being 0, or equivalently, we want to avoid the positive or negative square root of 3. So like I said earlier, when we were talking about these things, I'm going to be a little bit quicker about the basic algebra step there of adding 3, taking the square root. At this point, I hope that everyone who's here knows how that's meant to work. Where when we have that restriction, if we then want to describe from it the domain of the function g, we can again talk about this as being something like the set of real numbers without, where here we are removing negative root 3 and positive root 3. Or in set builder notation, this would consist of the set of x values such that x is not equal to plus or minus root 3. Again, it's essentially just taking this sort of thing and putting it with a little bit more of an exacting language as a set. Or, if we prefer to use intervals, the interval from negative infinity to negative root 3, along with the interval from negative root 3 to positive root 3, and I'm out of space, so I'm going to have a bad notation here, but we're also throwing in a union for everything past root 3 as well, because the only issues are at those 2 points specifically, so we can talk about it in any of these 3 ways. And then for our last example, which I'm going to be a little bit short on space for, but that's okay, because there's not actually that much to do. What we want to avoid there, not aviad, avoid is x squared plus 3 equaling 0. But if we want to avoid x squared plus 3 equaling 0, that means we subtract over the 3, take the square root, or that means we want to avoid x being plus or minus I root 3. And that's an imaginary number, or complex number without a real component, but the point here is that it's not something, strictly speaking, real in the mathematical sense. So we don't actually mind. When we're talking about domains, we're almost always talking exclusively about domains in terms of real values. Getting into complex stuff is a little bit beyond what we care about for this. So actually, we don't have any restrictions. In this case, we have that the domain of, I believe I called this H, is actually just going to end up being all real numbers, or in interval notation, the set of all things from negative infinity to infinity, because we don't actually mind if we can be restricted by complex things. When we're talking about a domain, we're only talking about real things, so we're fine. And then from here, what we're going to look at is trying to describe what goes on around these kinds of values, these kinds of break-off points, because they're the most interesting things to focus on for a rational function. And to do that, we need to introduce a bit of an exacting language, a bit of a notation for saying what happens as we get close to certain points, and that's what we're going to see next.